And good morning. So we will start this morning session. Well, as you have noticed, the first speaker was not able to come. So we begin with HACHEM SLIMANI from University of Bejaia in Algeria. He will speak about Nonsmooth, multi-objective, fractional, bilevel programming under generalized DI invexity. So, HACHEM, please.
Thank you. Ladies and gentlemen, good morning. I have a pleasure to present you the essential part of our paper entitled Nonsmooth, multi-objective, fractional, bilevel programming problem under generalized DI invexity. So, general bilevel programming problems with a single objective function at each level can be formulated as follows. Such problems have two levels objective functions. The upper level objective functions is the capital F. The small f, or simply f, is the lower level objective function. G is the lower level constraint functions. X is, X is the, it's called the upper level decision. Y is the lower level decision. So, bilevel programming problems are hierarchical optimization problems which combine decision of two decision makers, namely the leader and the follower. Formally, the bilevel programming problem is an optimization problem having constraints which are determined by another optimization problem. Thus, the upper level decision maker corresponds to the leader and the lower level decision maker corresponds to the follower.
Which is the first constraint? Subject to what? The first constraint.
Sorry?
Which is the first constraint? Subject to what?
Y
To-
or Y?
Subject to minimize fxy. Y belongs to the capital Y. The hierarchical process means that the leader makes a decision first and thereafter the follower chooses her strategy according to the leader's actions. In this process, the leader can influence but cannot control the decision of the follower. So the bilevel programming problem is very hard to solve because or due to its non-convexity and the implicity of its feasible set. For example, if all the functions are linear and the feasible sets are polyhedron, this problem remains non-convex. Thus, we can consider that such field or such a problem are very interesting for our conference, Generalized Convexity and Monotonicity. For this reason, this problem has received a large attention and it has been studied and developed by many authors. For extensive bibliography, the reader can refer to the monographs by Dempy and Bard and the bibliography reviews by Vicente and Calamay and several other references. In our paper, we have studied a non-smooth, non-linear, multi-objective fractional programming problem. Before presenting this problem, I try to give some preliminaries and definitions. Function f is said to be locally Lipschitz at x0 if there exists a neighborhood vx0 and a positive constant such that the relation 1 is satisfied. If f is a locally Lipschitz function at x0, the Clark generalized directional derivative of f at x0 in the direction d is given by the relation 2. And the one-sided directional derivative of f at x0 in the direction d is defined by the relation 3. It's clear that if 0x0d is greater than or equal to f prime x0d, we say that f is directionally differentiable at x0 if its directional derivative f prime x0 d exists finite in all directions. As a generalization of convexity of non-differentiable vector functions, Ye proposed the following definitions. If you have a function which is directionally differentiable at x0, f is said to be d-invex at x0 in the direction with respect to eta if for any x belongs to D, the relation 4 is satisfied. Note that each component of the vector function f is considered to be directionally differentiable in the same direction eta. However, this same direction does not always exist if we have functions that are not especially locally Lipschitz. So, in a previous paper of mine, we have considered functions that are not necessarily differentiable in all directions. Thus, we have introduced the concept of semi-directionally differentiable functions. This class of functions are, where no assumption or continuity are needed is an extension of locally Lipschitz functions. So, we say that a function f is semi-directionally differentiable at x0 if there exists a non-empty subset, capital S, such that f prime x0 d exists finite for all d in the capital S, belong to the capital S. It means that such functions are not necessarily directionally differentiable in all directions, but are only in some directions. In equivalent way, we say that f is semi-directionally differentiable at x0 in the direction phi if its directional derivative if prime x0 phi exists finite for all x belongs to D. It's clear that if you have a function which is directionally differentiable, then it is semi-directionally differentiable, but the converse it's not true. Thus, by using this concept, you have introduced the so-called div-invex functions. If you have a vector function f such that every component is semi-directionally differentiable in its own direction, thus we say that the f is div-invex at x0 on D with respect to eta I if the relation 5 is satisfied. Thus, we remark that in this, if we compare with the condition of Ye, this we have considered each component semi-directionally differentiable in its own direction instead of requiring the same directions. From this definition, in this paper, we have defined generalized div-invex functions. If you have a vector functions where every component is semi-directionally differentiable in its own direction, we say that the function f is pseudo div-invex at x0 with respect to eta I if the relation 6 is satisfied. And we say that f is quasi div-invex at x0 with respect to eta I if the relation 7 is satisfied. We use these concepts to establish necessary sufficient optimality conditions for the problem that we have studied in this paper. The problem is that you have studied, that you have considered in our paper is the following Nonsmooth and nonlinear multi-objective fractional bilevel programming problem. The objective functions, the upper objective functions is fractional vector valued. The lower objective functions is vector valued, and the feasible region is determined by inequality constraints. The particularity of this problem is that the involved functions are not necessarily continuous and then not necessarily Lipschitz functions. We give some definition for this problem. The constraint region of NMFBP is the capital S, which is defined as follows. The projection of S onto the upper level space is given by S capital X. The constraint region of the lower level problem LLPx for some fixed x is given by Sx. For a fixed x, S bar capital X denotes the weak efficiency set of the solution of the low-level problem LLPx. The induced region of the problem NMFBP is given by RIR. We have also used the following notation for fixed x and fixed y0. We denote by gxy0 the index sets of active constraints of the low-level problem. We note by gx tilde y0 the index set of non-active constraints of LLPx. Also, we note by gxy0 the cardinal of the set gxy0. What is a feasible solution to this problem, to the bilevel problem? If you have a fixed x, for a fixed x, if y is a weakly efficient solution to the lower level problem LLPx, then xy is a feasible solution to the problem NMFBP. What is a weakly efficient solution to NMFBP? x0, y0 is a weakly efficient solution of the problem NMFBP if y0 is weakly efficient to LLP x0 and there exists no another feasible solution of the problem such that the relation 8 is satisfied. To establish the Karush-Kantik necessary optimal efficiency condition to the lower level problem, we need to use the following constraint qualifications. If we have x and y0 and a function phi g, h bar is said to be satisfied with the I constraint qualification at x0 with respect to phi g if there exists x bar such that the relation 9 is satisfied. Thus, we have established the following Karush-Kantik type necessary efficiency conditions for the lower level problem LLPx. If you have y0 is a weakly efficient solution for LLPx for a fixed x, under some conditions of convex likeness and DI constraint qualifications, we obtain that there exists some Lagrange multipliers u and v such that the relation 12 is satisfied. This relation 12, we will use this relation 12 to transform the bilevel programming problem to multi-objective one single level programming problem. By using this, we obtain the following multi-objective fractional single level programming problem. We obtain it by replacing the lower objective function by its associated Karush-Kantik type necessary optimality conditions. Thus, this problem can be written in a simple form by using some changes of variables. Especially, we use variable z by which combine the original variables x and y and the Lagrange multipliers u and v. Thus, we write the problem in the simple form, which is denoted by MFP. This is clear that this problem is multi-objective fractional programming with inequality constraints. We have obtained some sufficient optimality conditions for a weakly efficient solution for MFP KKT will be a weakly efficient solution of the bilevel programming NMFBP. If we have x0, y0, u0, v0 is a weakly efficient solution to MFP KKT and some generalized DI invexity, we obtain that x0, y0 is a weakly efficient solution for NMFBP. Conversely, if you have a solution of the bilevel programming NMFBP, then under some conditions we obtain that this weakly efficient solution of MFP KKT. Thus, if you have a solution, if you have X0, Y0 is weakly efficient solution of NMFBP, then under the condition 2, 3 of theorem 10, and if the functions, the constant functions G bar satisfies the DI constant qualifications, then there exists some Lagrange multipliers such that X0, Y0 with V0 is a weakly efficient solution of MFP. From these two theorems, we can state that every solution that the weakly efficient solution set of MFP coincides with the weakly efficient solutions of NMFBP. To obtain necessary efficiency condition for the problem MFP, we need to use the following semi-constraint qualifications. We say that Z0 is, if we have Z0 be a feasible point of MFP and some functions theta I and phi G, we say that H is said to satisfy the semi-constraint qualification at Z0 with respect to Gi, theta I, and phi j if we have the relation 13 and 14 are satisfied. Thus, we have obtained the following Karush-Kantiker type necessary efficient condition for MFP. Thus, if you have X0 is local weakly efficient solution of MFP, and there's some conditions of convex lightness and semi-constraint qualifications, we obtain that there exist Lagrange multipliers such that the relation 18 is satisfied. We have seen that under some generalized DIV invexity and some appropriate constraint qualifications, if every weakly solution of MFP KKT is a weakly solution of the bilevel programming problem. Thus, we obtained sufficient efficiency condition for MFP. If you have, then the following theorem give us sufficient optimality condition for a feasible point of MFP to be a weakly efficient solution for MFP, and under equivalence conditions, the point should be a weakly efficient solution of the problem NMFBP. We have also obtained sufficient efficiency conditions for a feasible solution to be an efficient solution for MFP under generalized DIV invexity, which is given by the following theorem. As a conclusions, we said that we have considered a non-smooth optimistic bilevel programming problem in which the objective function of the upper level is nonlinear fractional vector valued. The objective function of the lower level is nonlinear vector valued, and the common feasible region is determined by inequality constraints. By using Karush-Kantiker type conditions associated to the lower level problem, we have reformulated the bilevel programming problem into an equivalent non-smooth nonlinear multi-objective fractional single programming problem with inequality constraints under appropriate constraint qualifications and generalized DI invexity assumptions. Thus, we have studied the obtained problem, which is a multi-objective single level programming problem with inequality constraints, but by considering each involved function is semi-directional differentiable in its own directions instead of the same directions. These involved functions are considered, are supposed not necessarily continuous, then not necessary Lipschitz functions, locally Lipschitz functions. Thus, we have established necessary and sufficient optimality conditions for a feasible point to be to be weakly efficient under generalized GI invexity. This some references for bilevel optimizations, some references of mine about the generalized DI invexity and the reference to the DI invexity of Ye. Thus, I finish my talk. Thank you very much for attention.
Yes, question, comments?